that were witnesses for me because I'm like, you heard it, I don't have to pick nothing. All right. Good.
Yeah, me too.
You know, if you ask questions, you want to do some work right away.
Well, good morning, all. It's first day after the 4th, so we're all tired, I think. So make sure that you turn in homework 1 before you leave at some point. I did take your quizzes with me on vacation with me, and they stayed in the bag the whole time. So I will grade them today and get the scores posted as soon as I can. I looked at the online submissions. I saw that most people had done it. So let's see. I will post solutions to the homework later today. Once I get back to my office, I should be able to get in once we're done with class here. Let's see. Online students, I did set up that submission place for you. So turn it in that way, or you can fax it or email it or whatever. The easiest way would be to turn it in through the Blackboard, but you guys here, you can just turn it in the old-fashioned way. This begins our kind of weird week. What that means is that the only time the on-campus students should come here is today. After this, don't come back unless we'll get back to that, except for maybe this Thursday thing. Later today, I will record another lecture going through some more of the Chapter 3 material. It'll be posted today, and you can watch it sometime between now and, say, Wednesday, and I'll set up an online quiz for you to do sometime between now and Thursday afternoon or something like that. Give you an opportunity the idea here is to continue moving forward with the material, even though I'm tied up with the summer youth stuff. So if you do have questions on any of the material in general, I will not be available from 9 to 10:30 and from 1 to 2:30 as I do these summer youth program things. So if you have questions or concerns, you can visit me anytime but those times. Now, as I indicated in an email last night, or very early this morning, one of the two, they're going to be trying to shoot this video of, I guess, cool Michigan Tech stuff. I don't know how else to describe it. In order to drum up some excitement for the university, one of the things they wanted to do was videotape our class. The only time that I can do it mixed in with the summer youth stuff is Thursday from 10:30 until 10:50. Are you folks available to come by and at least pretend to learn for 20 minutes? Sure.
I don't know. Probably.
I can probably arrange for donuts or something to be provided on the way in or way out or whatever. So we'll make something happen along those lines. I'll let the people in university marketing know that we'll be available, but only during that time, and I'll let you guys know through email or whatever if we're actually going to do that. So I have to find out if that time works into the videographer's time as well. So as a reminder, at least for now, definitely don't come on Tuesday. Definitely don't come on Wednesday. And if we come on Thursday at all, it's only going to be from 10:30 to 10:50. I'll let you know if we're going to come at all. Okay. If you have any questions on the homework, let me know. I would like to kind of cruise through some more of the material. I know there was an online student that had a request for a couple of problems to be looked at, and I'll post some fully worked out solutions later today. For now, I'd like to kind of move forward with this Lecture 3 material so that we just keep moving during this week. So, any questions on the schedule or whatever? I'll also post a quick homework assignment to continue moving on with this material as well. So, all right. We learned last week about some Ohm's Law stuff, about KCL, about KVL, and we used those things to do at least one circuit solution. And it was this ridiculous contrived process where we took and we reduced the circuit down, we combined all the resistors, and we found these voltages, and we found these currents, and we kind of built the circuit back up. And we can do that, but it's a pretty awful process if we were to try to do that as our only circuit analysis technique. And what we can start using instead is nodal and mesh analysis, which are the first two real circuit analysis techniques that we'll learn this semester. So the first one that we'll take a look at is node or nodal analysis. The basic idea here is we're going to look at all of the nodes within a circuit, and we're going to start writing some KCL equations, and we're going to introduce some node voltages. And what's interesting about this whole process is that once we have those node voltages solved for, we can then solve for any other circuit parameter that we're looking for. We can find the voltage across the resistor. We can find the current running through a resistor. We can find the power. We can find, whatever we'd like to do based on those node voltages. The next thing that we'll look at is loop and mesh analysis. In those, what we're going to do is we're going to write some KVL equations going around all of the different loops of a circuit. Once we figure out all of these loop currents, again, we have, at least in terms of an analysis tool, something that will allow us to figure out the voltages across the resistors, the currents running through the resistors, and so on. We'll start out with nice simple versions of the circuits, and then we'll move on to more complicated versions, which at least in part means we're going to start out with independent sources, and then we'll move on to dependent sources. And again, just like in the last chapter and that problem that we did at the beginning of class, we're always going to start out writing our equations and doing the analysis as though those dependent sources were independent. Then we'll write the controlling equation and then sort it all out in the end. But we'll look at those as we go. We've got a lot of examples that we can work out for these, and we'll try to get you through it. So again, we'll start out with nodal analysis. In general, these are interchangeable analysis techniques. You can use either one on any circuit. What you will find after at least some period of time is that certain circuits, based on what you're trying to find or the configuration of the circuit itself, kind of lend themselves better towards doing nodal analysis or lend themselves to mesh analysis. And one of the things that I'm almost never going to do, aside from very first kinds of quizzes and homeworks, I'll make sure that you can do both methods. But once we get to the exam, I don't care. Do whichever one makes sense to you, because in my opinion, the bigger thing is not just knowing, what is mesh analysis, what is nodal analysis, but which is the right one to use at any given time. That's engineering. Engineering is not using nodal analysis. Engineering is using the right tool at the right time. Okay, off the soapbox. Back to nodal analysis. The idea here is, again, what we're going to do is we're going to introduce all of these node voltages, and we're just going to name them creatively V1, V2, V3, V4, so on. And we're going to write a KCL equation at each one of those nodes. And once we have the KCL equations, there's going to be, if we have n nodes in our circuit, we're going to have n equations, and we're going to solve them simultaneously using the solution technique of your choice. Generally, I just plug them into my calculator and go. If you want to use Gaussian elimination or other methods, knock yourself out. But I just use my equation solver on my calculator. And that will give us all of these node voltages. And once we know all of the node voltages, we can solve for any other circuit parameter. So that is going to be our general flow of things. To be able to look at this one, we need to include not just the slides, but also this lovely diagram. And in this diagram, this particular circuit, we have all of the circuit parameters solved for already. I have to switch to a different marker. So we've got a 12 volt source. We've got nodes. One of the first things that we have to very clearly get a hold on as we start doing nodal analysis is how many nodes actually are there in the circuit. In this case, there are five nodes, but one of them we're going to call the reference node. And for purposes of our analysis, the voltage at the reference node is always going to be 0 volts. And so when I said a minute ago that if you have n nodes, you're going to need n equations, it's actually n minus 1 equations because we have 5 nodes in this circuit. Nodes 1, 2, 3, 4, and you could name that one 5 if you wanted to, but we're going to call that one the reference node, and we don't have to write an equation for that one. We're going to assume that the voltage there is 0. But in this case, we know this is 9 kilo ohm resistor, 6 kilo ohm resistor, 3 kilo ohm resistor, 4 kilo ohm resistor, 9 kilo ohm resistor, and a 3 kilo ohm resistor. And we know that, let's see, where do we have? This is VA, it's 3 volts. This is VB at that node, it's 3/2 of a volt. And this is VC, and it is 3/8 of a volt. This is the same, the voltage at node 1 is constrained to be the voltage of the source, so we know that one is 12 volts as well. So, it's not always the case that we know all of these voltages, and part of a nodal analysis is finding out what all of these voltages are in the first place. That's what makes it a problem-solving technique instead of just having the answer. But if we wanted to know, for example, let's call this V1. What is the voltage across the 9K resistor? What we can say is that the voltage across the 9K resistor is the difference, just like all voltage is a potential difference, the voltage difference between the point Vs and the point Va is the voltage minus Va is the voltage across the 9K resistor. And so then obviously what that means is that if there's 12 volts here and there's 3 volts here, then there's 9 volts across the 9K resistor. Fairly straightforward because the 12 volts at the source, 3 volts at VA, so there's 9 volts across that resistor. And then kind of duplicating the information that's already on the slide, if we wanted to know what is the current that's running around that particular part of the circuit, and call that I1. I1 is the voltage V1, the voltage across the 9K resistor, divided by the 9K resistance. Well, we kind of came up with an equation for that in terms of Vs minus Va, and this is going to be kind of the basic form for everything that we do in nodal analysis. We're going to take the difference between the voltages at 2 of our non-reference nodes and that has a resistance connected between it, and we will take the difference of those two, put that in the numerator, put the denominator in the bottom, and that gives us the current in a given node. Now this starts to get somewhat more complicated as we get into into nodes that have more branches coming out of them. For example, at node 2, we have currents I2 and I3 as well. At this node 1, it's very simple. The current coming in is the current going out, and that's just how it is. But at node 2, we've got 3 currents. Our KCL equation there would be something like, let's see, the current coming in gets the negative sign, the current going out gets the positive sign, and so simplifying right off the bat, we can say that I2 equals I1 equals I2 plus I3. And now we can start talking about what are, writing those in terms of our other parameters, and we'll look at exactly what that ends up kind of turning into. But this is the important form of the equation, and there's a little bit more of that on the next slide. In general, we've kind of got this, we can have a nebulous, if we had something going on, there's something in the circuit, and that circuit, there was a node M, and there's some voltage at that point M, and we've got some node N, and there's some resistance R with a current I running through it. Whatever else is happening in the rest of this circuit, it really doesn't even matter. If we want to know what that current I is, we take the voltage at point M minus the voltage at point N and divide it by the resistance. And that is the general form of everything that we're going to do for nodal analysis. Now, one of the things that we're going to have to try to do at some point is, if we're going to start, we've done the analysis at point M, then when we do the analysis at point N, we're still going to be talking about the same current. And I'm going to tell you how I do it, which I think makes more sense to me. But there's another way that you can do it, and sometimes you may see that in the solutions as worked out in the textbook and so on. But I will show you kind of the way that we do it. Just as a brief aside, as I've already noted, we don't always know what the node voltages are, and in fact that's the whole point of using nodal analysis. But we always know what the voltage is at the reference node, and we're always going to call that 0 regardless of what it might actually be. You may have a circuit where the reference node isn't actually at 0 volts, but once you've figured out what these relative voltages are, all you have to do is say, well, now this is at 3.3 volts, so just add 3.3 volts to everything that you have. So here is the easiest possible way of doing some nodal analysis. And there's a bunch of work on the screen that you can take a look at, but I'm going to duplicate most of it on the paper. So here is a simple circuit that we could analyze in the fashion that we did last Thursday. But we have grown beyond that, and we have better things to do with our time. So we've got, and we're going to start out with this all in terms of a bunch of variables, and maybe we'll plug in numbers later. The current source over on the left-hand side generates some current IA. This one generates some current IB. There is a resistance R1, resistance R2, resistance R3. The next thing that we have to do is establish how many nodes do we have in the circuit, so we can have some sort of idea of how many equations that we need to write for the circuit in the first place. There is clearly a node here, clearly a node here, and then there's one big node across the bottom. And it kind of tends to be the case that we will stick the reference node along the bottom. You could stick it anywhere you want, but kind of by tradition we stick it along the bottom. And remember that this point and this point and this point and this point are all the same node because there's nothing connected in between them. So there's 3 nodes in the circuit, node 1, node 2, and one of the reference nodes. What that means is we're going to have to write 2 simultaneous equations to solve for all of the voltages in the circuit. Now if we write the KCL equation at node 1, we have a current that's rolling into the node of IA, and say that's negative IA because it's coming into the node. Then we have, let's call this current I1 to be consistent, I1, and this current is I2. We've defined them as both leaving that node. Again, it's something that we can say, hey, they're leaving, and if we do the math, and if we end up with a negative result, that's okay. It just means that the reality of the circuit is that the current is running into the node. Or vice versa, you may define it as running into the node. The math works out that it's actually coming out of the node. It doesn't really matter. So for convenience sake and for the not introducing too many negative signs, we'll just define them as leaving the node. And so that means that the current running in plus the current leaving I1 and the other current I2, the sum there is 0. Now, easily, I mean, this is the kind of thing that's going to be given to you in the problem statement. We know what this is. It's an independent current source. So we know that. What we don't know is what are the values for I1 and I2. And so we need to write the node equations to make that happen. And we've got two good examples of writing these node equations. So let's start with the first one is that for over R1, the current I1 is given as the difference between the voltages at the two node endpoints of that branch. So we've got some voltage, and we'll call it V1. And at the other end, we've got the reference voltage. Well, we declared on the last slide that the reference voltage, we're going to assign the value of 0. So we just say V1 minus 0. Now, if it helps you, you can go ahead and you can stick in that minus 0, at least to start, and you can do it forever if you want to. But out of convenience sake, most people will start dropping that minus 0 and saying, as long as it's connected between a node and the reference node, I can drop the second voltage and just ignore it. And that's between, and those two voltages have a resistance R1 between it. I2 is a little different. We've got some voltage at node 1, and we've got some other voltage at node 2. We'll call this one V2, and this one's again V1. And we've got V1 minus V2 over R2. And so we can plug these things back up into this original equation. And so that gives us our first equation. IA is still a constant, and we've got I1 and I2 defined in terms of these node voltages. So that's one of them. I'll pop up the slide so you can take a quick look at that. The next thing that we're going to have to do is we need to write a node equation for node 2. We've done node 1, now we need to do node 2. The equation is remarkably similar. We've got some current I2 that's coming into it. So if we can flip back over to the document cam now. We've got the current I2 that's running into node 2. So that's negative I2. And we've got a current source that's leaving, that's IB. That's going to be constant. That's nice. And then we've got, we'll call this one I3. That's leaving the that's leaving node 2. That's also going to be positive, and so that one equals 0. So here's one of the places where you can do it a couple of different ways, and I'm going to give you the way that makes sense to me. We've already defined I2 as being V1 minus V2 over R2. And so I don't particularly, what I like to do is to always write my node equations kind of with the thought in mind of put the node that I'm working on as the first thing in the equation in the numerator. So I want to call that V2 minus V1 over R1 or R2, and that's okay. That ends up working out. Obviously, if we take and multiply what we've already defined I2 to be, and multiply it by -1. This transforms to this. So you can do it either way. You can say, well, I've already defined what I2 is. It's this quantity of V1 minus V2 over R2, and I can put it up there and I can put a negative sign in front of it. That's one way to do it. I find that complicated. I find that I will lose the negative sign or whatever. And so I like to say I'm working at node 2. Node 2 goes first in all of my subtractions in the numerator. And so I'm going to say V2 minus V1 over R2 gives me the current R2. But it works out mathematically either way you look at it. IB is a constant. And I3, we've got a resistor R3 that's connected between node 2 and the reference node. So that would be V2 minus 0 over R3. KCL says that equals 0. So what we have are two equations. We've got this first equation. So this is the KCL at node 2. we've got two equations, two unknowns. V1 and V2 are our only real unknowns. Everything else is going to be a circuit parameter that's given to us in terms of what are the resistance values, what are the values coming out of the current sources, IA and IB, and you just plug and chug those numbers. One of the things that I neglected to mention about when I do grade those quizzes and when I start grading problems like this is that, for example, on the quiz it's 10 points for that question. 8 of those points will come, 8 or maybe even 9 of those points will come from your circuit analysis. And I'm not going to heavily penalize you for math. The reality of most of the circuit stuff that we do is that there's not a whole lot of circuit stuff. And where you're going to mess up is not on the circuits, but on the math. And that's kind of, I don't want you to be penalized for just messing up on algebra, because that's not the point of the class. The point of the class is the circuit analysis. So as long as you write proper node equations or proper loop equations or whatever, I'm not going to heavily penalize you on the math, which makes my job in terms of grading your stuff a lot harder, but whatever. So we've got two equations, two unknowns. We can solve those and figure out what's going on in the circuit. Because once we find out what V1 and V2 are, we can figure out what the voltage is across R2, and then we divide that by the resistance, and we can find out what that current I2 is. So we can solve for power, we can solve for voltage, we can solve for current. Whatever we want to do, all of those things are now available for us to solve for because we have those node voltages. Again, you can solve that however you'd like. I really don't care. If you're going to use a calculator, that's just fine with me. Write out as much work as you can and say, well, I got to this point, then I plugged it into my calculator, and these are the numbers that I got for each of the node voltages. And that's fine with me. I don't care. Just show as much work as makes sense. The more work you show, the more that I have to work with. So. Again, if you have n nodes, you need n-1 simultaneous equations to make it happen. So let's take a look at this circuit. We'll add some values in and solve just to play around with it. And we've already got the KCL equations written. So let's take a look at what it looks like if we add in some values. So I'm going to redraw the circuit to make it a little cleaner. We've got that current source, a resistor, second current source, and this third resistor. V1, V2, this is a 6 kilo ohm resistor, this is going to be a 12 kilo ohm resistor, 1 milliamp current source, 4 milliamp current source, and a 6 kilo ohm resistor. So again, in this case, one of the things that is going to be personal preference on your part is going to be, what do you do with these constant current sources? Do you put them immediately on the right-hand side of the equation, and so that you can get the equation into some form where you just have like 6V1 plus 12V2 equals -6, is that the thing that you're going to work with? Or are you going to start out writing the proper version of the KCL equation where it all sums up to 0? It doesn't matter to me. You can do it again however you want. So we've got that first KCL equation is at this node V1. We're going to have the 1 milliamp of current source running in. So I'm going to take and I'm going to stick that on the right-hand side of the equation. Then we've got V1 and the reference node over 12K, so V1 over 12K. And then the other branch here is V1 minus V2 over 6K. So that's one of our KVL equations, or KCL equations. The other one is over here at node 2. Again, what I'm going to do is I'm going to say I'm working at node 2. I'm going to put node 2 first. V2 minus V1 over 6K. We've got 4 milliamps of current leaving. So let's stick that over on the right-hand side of the equation again. But because it was positive to start with, it has to be negative now, right? It was going to be positive on the left-hand side. Subtract negative, or subtract 4 milliamps from both sides. Second part is going to be V2 minus 0 over the reference node over the 6K of resistance there. Now to be able to solve these, what I'm going to do whenever I do these examples in class is to show as much work as possible. And for me, it helps to get these things in terms of a common denominator and stuff. But you can do it any way that kind of feels good. So obviously the common denominator here is 12K. So that's 1 over 12K plus 2 over 12K V1 minus V2. That equals 1 milliamp. And then we've got negative 1 over 6K V1 plus 1 over 6K V2 plus 1 over 6K V2 equals negative 4 milliamps. So the negative 1 over 6K from here, positive 1 over 6K from here, positive 1 over 6K from here. We could simplify this one further and say we've got 1 over 12K plus 2 over 12K V1. So we got 3 over 12K V1 minus 2 over 12K V2 equals 1 milliamp. This one simplifies down to 1 over 6K V1 plus 2 over 6K V2 equals negative 4 milliamps. And then you can solve. The solution actually ends up being, in this case, that the voltage V1 is negative 6 volts and the voltage V2 is negative 15 volts. All that means is that we had defined this reference node down at the what we would call the bottom of the circuit to be the lower potential, and that's not the case. The higher potential is actually down at the bottom of the circuit. The lower potential is up here at the top. That probably is could be guessed by virtue of the fact that the larger current source was pointing down. So now you can figure out anything else that you want. We could figure out the voltage between those two by subtracting V1 minus V2. So that would be positive 9 volts across the 6K resistor. Then 9 over 6K is going to give you the amount of current that's running through the resistor and so on. And that's nodal analysis with a constant current source. Constant current sources are nice because they just add a constant flavor to the equation, and that's all it takes to kind of really do it. So, so let's do one more quick example, then I'll have you guys do one. So we've got a somewhat bigger circuit. It's going to require a few more node equations. So let's see, R1 and R2, this is 2K, this is 2K, R3 and R4, this is 4K, this is also 4K, this is a 1K resistor, this is a 4 milliamp source, and this one is a 2 milliamp source. So again, the first question that we kind of have to ask ourselves is, how many nodes do we actually have in this circuit, so we can write the appropriate number of equations. Clearly a node here, clearly a node here, and then there's kind of, as the circuit is drawn, there's kind of 2 nodes here in the center, but there's nothing connected between those two, so this is really just one node, and we'll call that one V2. So we've got 4 total nodes. We're going to need 3 simultaneous equations to solve this circuit. So, first one. It doesn't matter the order in which you do these. So let's kind of do maybe the harder ones first, or the easy ones first. We've got V1 and the reference node with 2k connected between them. So we've got V1 minus 0 over 2k. We've got V1, and then we've got 4 milliamps of current leaving. So I'll say plus 4 milliamps. And then we've got V1 and V3 with 2k connected between them. So plus V1 minus V3 over 2k. KCL says that equals 0. Move on to node 2. Now we've got 4 milliamps of current that are running in, so we'll say negative 4 milliamps. We've got V2 over the reference node, and that's with a 4K resistor connected between it. So we've got plus V2 minus 0 over 4K. We've got a 2 milliamp current source leaving, plus 2 milliamps. And then we've got V2 and V3 with a 4K resistor connected between them. So we got plus V2 minus V3 over 4K equals 0. And these KCL equations can get, really big depending on the number of branches that are actually connected up to a given node. In this case, we had 1, 2, 3, 4 things connected up to it. In V1, we just had the 1, 2, 3 branches. For V3, we're also going to just have 3 branches and 3 terms in our KCL equation. So again, as we go back over the top of this one, I'm going to say I'm working at V3, so V3 is going to come first. V3 minus V1 over 2K for this top branch. We've got V3 minus V2 over 4K for this branch. And then V3 and the reference node are connected with the 1K resistor. V3 minus 0 over 1K equals 0. So those are the KCL equations. Those are all of our node equations that we've written. And so that's, again, that's the end of the circuit analysis that we actually do for this. Everything past here is math. Just can you solve the simultaneous equations and get the right number? This is the important stuff. This is kind of the new stuff. So for the sake of time, let me jump right to the end and say V1 in this case solves to be 0.245 volts. V2 equals 4.35 volts. And V3 equals 0.691 volts. And it's just a matter of simplifying each of these equations. And we'll do enough examples that I'm not going to worry about that one too much, unless you guys really want to see it worked out. No? You're good? Okay. So, all right. Here's one for you guys to try, at least real quick. All I want you to do in this case is to write the node equations. You don't have to solve them. All you have to do is write them. If you want to, you can simplify them down into something where it's, there's just a small coefficient on each one of the node voltage terms. Two milliamps, 4 milliamps, 6 kilo ohms, 12 kilo ohms, 6 kilo ohms. So the first thing before we get into it, to make sure that we're all on the same page, how many nodes do we have in this circuit, and how many equations are we going to have to write?
2 and 3 nodes.
3 nodes with 2 equations. There's a node here, a node here, and a node here. We'll call this one the reference node. Call this one V1, V2. And so take, say, a minute, 2 minutes, write up the node equations at V1 and V2. So we got two equations. The first one, we've got 4 milliamps of current that are coming in. So we'll say that's negative 4 milliamps. We've got V1 in the reference node. So V1 minus 0 over 6K. And then we've got V1 and V2 connected with a 12K resistor. So that's V1 minus V2 over 12K. That equals 0. If we simplify this one a little bit, put the 4 milliamps on the other side, find the common denominator, we've got, of 12, we've got, so this would be 1 over 6K, or 2 over 6K, this would be 1 over 12K for V1, 3 over 12K is 1 over 4K, so we've got 1 over 4K V1. I apologize for my ridiculous inconsistency between using capital and kind of script V's. I don't do it on purpose. But so we simplify the V1s down. We get 1 over 4K times V1 and 1 over 12K V2. And that equals not 0. It equals 4 milliamps. Second equation, similar. Again, my philosophy, I'm at node V2. I'm going to put node V2 first. So we got V2 minus V1 over 12K. I've got the 6K resistor connected between V2 and the reference node. So that'll be V2 minus 0 over 6K. And I've got 2 milliamps of current leaving. Let's take one shortcut and say we'll put that on the other side with the negative sign. Simplify that one down and we get negative 1 over 12K V1 from this part of the term here. And then we've got, similarly, we've got the 1 over 12K, and then this will be 2 over 12K, which gives us a total of 3 over 12K, or 1 over 4K times V2. And that equals negative 2 milliamps. Someone pointed out in the past that this is actually, if you have, if you were planning on doing kind of matrix solutions to these simultaneous equations, there is an easy way to solve this form of the equation, because you can see that there's a pattern, a consistent pattern. We've got the 1 over 4K times V1 and a 1 over 4K times V2. Negative 1 over 12K V2, negative 1 over 12K V1. And there's a simple equation, I think, that you might be able to find in your linear equations book, linear algebra book, that makes it so you can just plug in some numbers, and it only works when it's got this kind of reflexive nature to it, so you don't have to do the full matrix arithmetic to figure out what's going on. Again, if you're just going to plug it into your calculator, what difference does it make? So those are the node equations. If you're curious, if you plug that in, you get 13.71 volts for V1, and V2 is negative 3.43 volts. If you wanted to plug them in, make sure that you did the math right. Let's do one more quick example and try to work along with me on this one. So maybe I can get you guys to help me out and holler some of these things. So I'll give you one. Let's see. Let's put in the 4 milliamps, 2 milliamps, 1 kilo ohm, 2 kilo ohms, 4 kilo ohms, 1 kilo ohm. Okay. How many nodes do we need to write equations for? Three. Correct. Yep. We've got 4 total nodes in the circuit. One's a reference node. We'll call this one V1, V2, V3. So we need 3 equations to write. Again, we've got 4 milliamps of current coming in. That would be negative, so let's hold on to that one, put it on the right-hand side of the equation when we're done. V1, V2, 2K between them, V1 minus V2 over 2K. V1 and V3 with 1K between them, V1 minus V3 over 2K, or 1K, and that equals the 4 milliamps of current. So that's one equation. Second equation, I'm at V2. I'm going to put V2 first in my numerator. So we got V2 minus V1 over 2K. V1 or V2 in the reference node. V2 minus 0 over 1K. V2 and V3 with 4K between them. V2 minus V3 over 4K equals 0. Last one at V3. Again, V3 is the node I'm at, so I'm going to make that my, that's going to come first in my numerator, so V3 minus V1 over 1K plus V3 minus V2 over 4K, and 2 milliamps of current leaving, so equals negative 2 milliamps. So simplifying things down, common denominator here is going to be 2K, so this is going to be 2V1 minus 2 over 2K. So we've got, in terms of the V1s, we've got a 1 over 2K and a 2 over 2K, so it gives us 3 over 2K V1. The only V2 term is this negative 2K, so negative 1 over 2K V2. And then we've got a negative 2 over 2K V3 equals 4 milliamps. Here the common denominator is going to be the 4. So this is going to be 4 over 4K. These will be 2. So in terms of V1, we've just got the negative 2 over 4K. V1. V3 will be the easy one because it just shows up in this one term. So 1 over 4K V3. And then we've got a 2, a 4, and a 1, so that should be 7 over 4K times V2. Denominator here is going to be the 4K, so we have 4V3, 4V1. Got negative 4 over 4K V1. V2 is negative 1 over 4K times V2. And V3 is going to be 5 over 4K, right? Equals negative 2 milliamps. So in that form, you can put it into a matrix, or you can put it into an equation solver, or whatever. I think that your calculator is smart enough to, if you wanted to, you don't need to try to find the common denominator and write it out, as long as you just pull the terms out. And so an alternative form of this first equation would be, say, well, there's a 1 over 2K plus a 1 over 1K V1. And then for V2, there's just a 1 over 2K V2, and there's a negative 1 over 1K V3 that equals 4 milliamps. So you can do it that way too. It doesn't really matter. Whichever way kind of makes it easiest for you. Plug it into your calculator, and what you get from those 3 simultaneous equations is that V1 equals 5.4286 volts. V2 equals a nice round 2.0 volts. And V3 equals almost pi volts. once you run the numbers. So that's nodal analysis with constant current sources. We'll take a look at least one quick example with a dependent current source because well, we need to feel comfortable with it. But I think I'm only going to do one example of this just to get through it. And again, the basic flavor is going to be write the equations as if they were constant in the first place, as if it was an independent source. Take care of all of write the controlling equation, plug and chug from there. So here is our circuit containing a dependent source. We've got one independent source. We've got a couple of resistors. Here's our dependent source. And a final resistor. We have two nodes that we have to solve for in this particular circuit, V1 and V2. And the circuit parameters, 10 kiloohms of resistance, 4 milliamps of current, 10 kiloohms of resistance, 10 kiloohms of resistance, 2 times I0 amps of current, and I0 is the current that's flowing down through the 10K resistor. So, step one, write the node equations as if this was an independent source. We know how to do that, so let's just write them. At V1, we have V1 connected to the reference node with a 10K resistor, so V1 minus 0 over 10K. We've got 4 milliamps of current rolling in, so let's put that on the right-hand side of the equation. And then we got V1 minus V2 over 10K. So that one's not even any different. Doesn't affect us in any way. For node V2, we've got, I'm at node V2, so I'm going to put that one first. I have V2 minus V1 over 10K. V2 minus V1. Okay. I've got V2 and the reference node with 10K hooked between them. V2 minus 0 over 10K. And now here's where we act like it's an independent source. We have 2I0 that's flowing out of it. It's a current source. So say plus 2I0 equals 0. So now we've got our node equations. Unfortunately, we've got two equations and we've got three unknowns. So we need an additional equation in terms of unknowns that we already have in order to finish up these equations. So what is that unknown? It's the current I0. What is I0? Well, it's the current running through the 10K resistor over on the far left side. And what is the voltage, or what is the current running through the 10K resistor? Well, it's the voltage across the 10K resistor, which by my estimation is V1, or V1 minus 0, so it's V1, and divided by the resistance of the branch that's flowing through, 10K. We already kind of figured that out. That was this first equation over here. But now we formalized it. Now we can take and we can plug this result back into that first equation, or the second equation that we wrote, transform that. I don't want to try to do too many simplifications, but so we've just got V2 minus V1 over 10K. We've got V2 over 10K, and we've got 2 times V1 over 10K equals 0. So now, between this and this, we have two equations, two unknowns. Do the same simplifications, do the same solving, and we've analyzed our circuit with the dependent source in it. Just, I guess for the record, kind of get, I guess we get 2 over 10K times V1 minus 1 over 10k V2 equals 4.0 milliamps. And this one simplifies to, we got 2 over 10k V2, and then this was a negative V1 over 10k. This is positive 2 over 10k V1, so we just get 1 over 10k V1 plus 10 over 10k. So those are your two final equations. Solve those simultaneously, and that gives you your solution. And then you can figure out, if you wanted to, what is I0, what are the node voltages. Works out in this case that V1 is 16 volts, and V2 is a negative 8 volts when you run those numbers. Does that make sense at what we did there? Write the KCL, or write the node equations as if the dependent source was independent, and we just said, well, it's a current source and it generates 2I0 amps of current, and so we put it on this side with the positive sign because it's flowing out of the node. Then we write the controlling equation in terms of some other circuit parameters that we have already. In this case, we know that it's the current that's running through the 10K resistor, which is and the current would be the voltage divided by that resistance. Okay, so all of that has just been independent current sources. The next thing that we need to look at are voltage sources. Voltage sources can do one of two things to our circuit. They can either make our circuit really, really easy, because when we know that we're connected between one of the non-reference nodes and the reference node with that voltage source, we don't have to do anything. We know what the voltage is. It's constrained by the voltage source. If there's node V1 connected down to the reference voltage with a 12 volt source, well, the node voltage V1 is 12 volts. We don't have to think about it. And so that makes life really easy. And it puts in this one more constant into our equations. We actually can skip entirely, regardless of the number of branches that might be coming out of that particular node. We don't have to write any more equations. We just say V1 equals 12 and we're done. It can be nasty, though, if you have that voltage source connected between two non-reference nodes. And we have to introduce this kind of goofy concept of a supernode in order to make it work. I think we'll have to see what happens in terms of time today, but we may or may not get to the idea of the supernode. Let's see. So here is an example circuit. The equations are written off on the slide, so but we'll duplicate the work here. Here is our circuit. We've got 12K resistor, another 12K resistor, and in here we've got two independent voltage sources hooked up opposite ways. Doesn't matter. It's a academic exercise anyways. So 12 volts, 6K resistance, 6 volts, 12K resistance, 12K resistance, 9K resistance, and there's our circuit. Now we look at this and we can say pretty certainly we've got 4 nodes total. We need to write 3 equations to be able to solve this. But 2 of our equations are going to be really, really simple. They're just going to be V1 is connected between itself and the reference node with this source, and so V1 is constrained to be exactly 12 volts. We don't have to do any more analysis. We don't have to say V1 minus anything else. We're done. We don't have to do any further analysis at V1. Similarly, over here at V3, we don't have to do any real analysis because, again, it's hooked up with an independent voltage source. It's -6, and we're done. The only real node equation that we have to write is V2. Now here's a place where you have your kind of option on how you want to do this. You can write out the equations and say, well, I have names for these nodes. I'm going to stick to the process and say V1 minus V2, V2 minus V3, and all that stuff. Or you can say, I know what those voltages are. Why even bother writing the equation out that way? Both versions are on the slide if you want to take a look at it. What I will normally do is if I know what V1 and V3 are, I'm not going to bother sticking them in the equations anymore if I can help it. So I'm just going to say, well, V2 and V1 are connected, so that's V2 minus 12, because that's what V1 is, over 12K. We've got V2 in the reference node, V2 minus 0 over 6K. And then V2 and V3, here's where you got to be a little careful. V3 is negative 6 volts. We have V2 minus a negative 6 volts or plus 6 volts over 12K equals 0. So now we've got one equation, one unknown. You know, a simple equation solver will do that, or you can work it out by hand. But that's how independent sources can be pretty nice. Let's do one example from start to finish, and just so you're feeling comfortable with independent sources. $6K, 6K, 3K. The circuit parameter we want to look for in this case is the current I0 running down through the 3K resistor. We've got a 6 volt source here and a 3 volt source here. And our first question has always been, how many equations do we need to write? How many nodes are there in this circuit? Well, technically there's 4 nodes, but we don't, strictly speaking, even need to introduce these nodes because, well, we know what the voltages are. And so we can simplify our lives and really say, well, I know this one, so there's really just one equation to write at this point. Since we've got current I0, let's call this one voltage V0 just for convenience sake. That's the only equation that we have to write. We've got V1, or V0, minus the voltage here, 6 volts, over the 6K of resistance. We've got V0 on the reference node, V0 minus 0 over 3K, and V0 minus 3 over 6K equals 0. So we can simplify all this out. We've got V0 over 6K minus 6 over 6K plus V0 over 3K plus V0 over 6K minus 3 over 6K equals 0. Common denominator here is going to be the 3K. This is 2V0 over 6K. So we've got 1, 3, 4 over 6K times V0 equals, we had negative 6 over 6K, negative 3 over 6K, it's negative 9 over 6K. Put that on the other side, so we got positive 9 over 6K. Multiply both sides by 6K to get rid of all that nastiness. So we got 4V0 equals 9, so V0 equals 9/4 of a volt. Current I0 is the voltage V0 divided by the 3K of resistance. And we know what voltage V0 is. It's 9/4 of a volt. 9/4 of a volt divided by 3K of resistance. And using my cheater notes, I see that that is 3/4 of a milliamp. So independent sources can be really easy. can also find where they're going to be crummy and they're going to make our life a lot harder. And so when you find a voltage source connected between two non-reference nodes, then we're going to have to introduce what we call a supernode. One thing that it is going to do is it's going to make it so we kind of, our KCL equations or our node equations are going to be a little smaller, but yeah, it's going to be it's still going to be kind of nasty. And we're going to still have to write the same number of equations, but one of them is just going to be saying, look, the difference in the voltage between these 2 points is constrained to be the voltage of the source itself. So we introduced this supernode. And it was kind of handy that in the year that I was putting together these slides that Superman Returns was the big summer blockbuster, because it was really easy to find Superman logos. So let's look at an example of a circuit where we do have one of these supernodes. So here is our problem. We've got a voltage source that's connected between these two non-reference nodes. And this one is also kind of interesting because it has this mix of the independent current sources as well as the voltage sources. 4 milliamps of current here, 6 milliamps of current here, 6 kiloohms of resistance, 12 kiloohms resistance, 6 volts, V1, V2. And actually, one thing that you can do in this case, if you wanted to, is you could say, well, I don't want this to be the reference node. I want that to be the reference node. Hey, that's fine. Knock yourself out. It's really okay if you want to do that because the reference node doesn't have to go down at the bottom. That's one way to solve it. But it may be the case that you have multiple voltage sources connected between multiple non-reference nodes, and you can't use multiple reference nodes or anything like that. So in this case, you could change the problem. You could be clever and say, well, I don't want the reference node to be down at the bottom. I want it to be up here. Save yourself maybe a little bit of heartache. But that doesn't give us any good examples to work with. So what we're going to do is we're going to kind of put this dashed line and say, this is our supernode. It's composed of multiple subnodes, and I'm going to write a single KCL equation or a single node equation out of that as if it were one single node. And so let's write the KCL or the node equation. There's only going to be one of them now that we've reduced our circuit that had 3 nodes down to really just having 2 nodes. One is the reference node, one is the super node up here. So we've got 6 milliamps of current that are running in, so negative 6 milliamps. We've got, now this is where it's going to be a little weird. Whenever we get to the branches that are connected to the specific subnodes of our supernode, write the equation just kind of normally. And so normally if we were looking at this, what is the current running through this branch? Well, it's the node voltage V1 connected to the reference node with a 6K resistor. So that's going to be V1 minus 0 over 6K. On the next one over, we skip this branch because we can't figure out what's going on there necessarily, at least now. Not until we figured out what these reference voltages are. So we skip that branch, come over to here. We've got V2 connected to the reference node with a 12K resistor. So V2 minus 0 over 12K. And then we've got 4 milliamps of current leaving, so plus 4 milliamps equals 0. And so we can obviously simplify that down, take and say, well, negative 6 milliamps and the positive 4 gives us negative 2. Put the 2 on the other side. We have V1 over 6K plus V2 over 12K equals 2 milliamps. Okay, that's fine, but unfortunately, we've only got one equation. We've got 2 unknowns. We've got to write one more equation. And the equation that we need gives us the relationship between the 2 subnodes in the supernode. And that is, when we look at this, we say, what this voltage source tells us is that V1 is 6 volts higher in potential than V2. And the way that we'll express that mathematically is to say V1 minus V2 equals 6. If the nodes had been switched, or if the polarity of the voltage source had been switched, for example, if this had been the negative terminal and this had been the positive terminal, we would have said V2 minus V1 equals 6. Not a big deal. So now we've got two equations, two unknowns. You can solve it in any way that you want. The kind of the traditional way to do that is to say, well, it depends on which one of these that you solve for depends on the circuit parameter you're looking for. So let's say, we'll call that one I1, call this one I2. Just for the sake of example, if the problem said, give me I1 or give me the power in the 6K resistor, well, I would probably want to have everything solved for in terms of V1 so that I find out what the node voltage V1 is. If it's asking for I2 or the current through or the power absorbed by the 12K resistor, I probably want to solve for V2 so that I can make that work. So you've got three different options. You can just use that, which is not particularly useful. You can say that V1 equals V2 plus 6, or that V2 equals V1 minus 6. And then you just take these two things, put it up into this single equation that you wrote for the KCL at the supernode, and solve for the parameter that you're looking for. Then you can, if you want to, you can go back once you figure out what V1 is and figure out what the difference is between those two, V2, and do the solution. So I don't have time to start out with the supernode analysis. I've got another example of those. And then we'll take a look at how do we deal with dependent voltage sources. So that's the things that we'll take a look at when you're not here. And hey, if you're not busy from 2:30 to 4, you can come and learn in person. And so I don't have to talk to an empty room. But, you know, I can imagine that you can only take so much circuits in one day. So we'll be back here at 2:30 if you want to be. Otherwise, there will be a video for you to watch sometime between now and Wednesday afternoon kind of time frame. If you have any questions, let me know. I'll have a homework assignment posted for you shortly. I'll have the solutions from homework 1 posted also shortly on Blackboard. And I will grade your quizzes as quickly as I can. So, I will not see you again until Thursday, maybe Monday, definitely. Have a good one.